please hit subscribe.
This problem appears at the qualifying examinations for applicants for Japanese government or MEXT scholarships 2020. This problem is from the 2020 physics questionnaire for the undergraduate scholarships. The answer key and original questions are linked in the description. Problem 5 reads, an ideal gas undergoes the cycle shown in the PV diagram of figure 1-5. Find the net thermal energy added to the system during one complete cycle. Let's review some ideas that will be helpful in the solution of this problem. First is thermal energy. Thermal energy is the kinetic energy, the average kinetic energy of the particles in the system. And so the faster and the more massive the particles are, the more kinetic energy there is. And we can actually measure the average kinetic energy of the particles using a thermometer. The temperature is known to be directly proportional to the average kinetic energy of the particles. We're not going to show it here, but we'll have to keep that in mind. And that is a well-known fact from statistical mechanics and thermodynamics. So temperature is a measure of the kinetic energy, the average kinetic energy of the particles in the system. Next is the first law of thermodynamics. It says that the change in internal energy of the system, equals the amount of heat coming in the system minus the work done by the system to its environment. So that's the work coming out of the system. And here, the heat in, this term here, is what actually adds to the thermal energy, because it's the heat here that actually raises the temperature, thereby raising the thermal energy, or the kinetic energy, the average kinetic energy of the particles. And then we also recall that internal energy is a state variable. So internal energy is the sum of all the energies of the particles in the system. So it's in the micro scale. Each particle will have a kinetic energy, potential energy associated with it, like chemical potential energy, electrostatic potential energy. So the sum of all those energies, both kinetic and potential, that is what we call the internal energy of the system. Now, internal energy is known to be a state variable. That means that it depends only on two other state variables, which is temperature, volume, and pressure, any two of those. So in this problem, we're dealing with pressure and volume because it's a PV diagram. And what that means is that the internal energy of the system depends only on the P and the V. And the corollary is that in one thermodynamic cycle, any thermodynamic cycle, the change in internal energy would have to be zero. The reason for that is a cycle is one where you begin at a certain pressure and volume, certain P and V value, and then there are several processes in the way, and then it goes back to the initial P and V values. That means it goes back to the initial state. Now, we have said that the internal energy is dependent only in the P and V values. So if you have a cycle, the initial internal energy is the same as the final internal energy, because the initial P and V value is the same as the end P and V value if it's a cycle, because that's what a cycle is. The initial P and V value must be equal to the final P and V value. And because they're equal, internal energies are equal at the beginning and at the end, then there is no change in the internal energy. So this term here actually goes to zero. That's what we'll use in the solution. And lastly, we'll have to think about PV work because we have a work term here, and that is known to be the area under the process curve. So if you have a process that goes from left to right, then that's a process where the system is doing work on the environment. So that's work out if it's from left to right. you can imagine that the volume increases during that because there is less volume on the left and higher volume on the right. And if we have a reverse process, meaning from right to left, then we have a case where the system is experiencing work from the environment. So the system, the work is going into the system, and that's why we say work in here. Now we need to find the net thermal energy added to the system, and that will be this term here, the heat in. That's the net thermal energy added. So that happens in this part of the cycle. So this cycle will have three parts, this arrow, and this arrow. Now, if it's a cycle, that means you can start anywhere and end anywhere. So for convenience, let's start here where the pressure is P naught and the volume is V naught. The first process is an increase in pressure, but constant volume. So from here to here. That means that the temperature increases during this process, and that is required by the ideal gas law. And so in this part of the process, this is where heat comes in. So there is heat in this process here. Then in the second part, this branch here, the volume actually doubles. And so we know that work is also done in this process. And then coming back to complete the cycle, we have a shrinking of the volume and also probably a change in temperature. And that is our process. And now we're only interested in the heat in for the first question. So we have to use this bit here. The change in internal energy equals heat in minus work out. So the change in internal energy, because this is a cycle we're talking about for one complete cycle, that's 0. And in this case, let's call the internal energy U sub int. And so if we use the first law of thermodynamics, we have 0 equals Q in is, let's call the heat in Q in and the work out W sub out. So we now have this equation from here. Now we can solve for Q in because that's what we're interested in, and we get this. Now we just have to solve for work out right now, and we can do that from this diagram here. So the work done by the system, work out of the system, is actually the area under the curve. So that's what we said here, the area under the curve. So if it's going to the right, that's a positive work. So that's the area under this. So that's going to be the area of this entire rectangle. So this area here under this split here. Now that is for this process. It's for this process. For this process, the first process, the volume doesn't change, and so also the area under that is 0, so nothing. There is no effect on the work for this first process. Now for the last process, this process here, let's give that a different color, let's say blue. For this process here, the area under that would be this. And also the direction is going there, so it's a negative work done by the system. So this is negative. So we have to subtract this area. The blue area must be subtracted from the red. And so we will be left with this area here. So we just need to find the area here. But we can do this, we can do that area from geometry, right? Because that's just a triangle there. And so we use the following. We use 1/2 base times height. So base is just, this is base and this is height, right? So the base would be 2v sub o minus v sub o. So that's just v sub o. And height is just 2p naught minus p naught. 2p naught minus p naught. And 1/2 base times height is the area of this triangle. And so that is just equal to this quantity, 1/2 P naught V naught, which is this answer here. If you learned something new today, please help my channel by clicking the subscribe button and the bell for the notifications. See ya!